All right. Welcome everyone to Lab 8, Binary Trees. Some announcements before we get started. Project 3 is due November 16th. That gives you 6 days. And then the autograders, 12th and the 19th. And then the written is due Friday, as always. If you haven't started the hash map autograder, it's due this Friday. Make sure you get started. The autograder is pretty cryptic on when you have wrong output, and it doesn't really tell you much. So it's not the greatest debugging tool. And I will also be holding an office hours for Lab 7 autograder, either Thursday or Friday for all of those procrastinators out there. And we can kind of step through the logic flow together. But regardless, try to get it started before then, and then maybe use that as help if you need to debug. Any questions on announcements? Cool. Okay, so let's talk about last week's written problem. Essentially what we had was a vector of strings for sentences. And for each of those words in the vector of sentences, or each of those words in the vector of strings, we had to, if possible, replace it with its shortest prefix. What is its shortest prefix? Well, we were given a vector of strings for all the prefixes. So, for example, the had no prefix in the vector of prefixes. So in the output vector, we just kept the same word. However, cattle does have a prefix, and its shortest prefix, well, its only prefix, but also its shortest, would be cat. So we replace cattle with cat in the output vector. Anybody want to explain how they did this? Okay, I guess I will. So, going through this, what I would think initially is, okay, I'm gonna have to iterate through every word in sentence. And for each word, see if it has a shortest prefix. So my initial thought process is, well, if I'm looking for the shortest prefix, I could just slowly build up a word, see if T is in the prefixes. So I would iterate through prefixes and see if it contains just a T. Then, build up T to TH, see if TH is in the prefixes. And you keep on checking until either you finish the word and there's no prefixes, so you just output that to the output vector, or you find a prefix and then you break out, right? Because you want to find the shortest one. You don't want to find any other one. So then that would be my initial thought. And then after that, it's like, do I really need to do a linear iteration through the prefixes vector? I'm just looking to figure out whether or not this word that I'm creating is hit the vector. So I can do that in O of 1 time. And I can just create an unordered set for my prefix vector so that I can quickly look up, is T in there in O of 1? Is TH in there in O of 1? But, there's an asterisk with that O of 1. Remember when you are hashing strings, it's not O of 1 to hash a string, it's O the length of the string. So we'll see that when we come back to the complexity. So let's look at the solution. So the prefixes vector was created using an unordered set, which is, remember, just an unordered map, but there's no value. It's pretty much just a key, and it'll tell you whether or not the key is in the set. So we have this unordered set of just prefixes, the strings, and then we create an output vector right here. And then we iterate through all the words. And for each letter of each word, we create a new string and we add that letter to the string. So we're slowly building up our word. You know how we did T, then TH, then THE. And every time we add a letter to this concatenated string that we're creating, we check to see if it's in the set. And if it's in the set, then we just break. Because that means that we found a prefix and we can push back that prefix. If we never find a prefix, then, we're going to iterate through all the letters and our prefix string is just going to be the word. So when we push that back, it's going to push back the entire word without a prefix after that for loop. Now let's talk about the complexity of this. So to create our unordered set, you have to iterate through all of the strings and hash that. So you might say, well, there's, in this case, I think, is it M? There's P prefixes. Wait. I think that's wrong. So there's P prefixes, and we have to iterate through all the prefixes to hash them into the set. So you'd say, okay, well, there's P of them. Each one's O of 1, so it's O of P. But remember, they're strings, so we have to multiply that by the length of the prefixes, which is M. The length of the longest prefix is M. So to create that unordered set, it would be O to the P to the times M. Then we have to iterate through each word in the sentence, which is going to be, let's just say N is the number of words. And then each letter of each word, which we just said was M, worst case, was the length of a letter. And then we also have to call that set, which is going to give us not O of 1, but O of the hashing length that we're calling it, the key length, which in this case is O of M. And then remember from earlier in the semester, these are not sequential, so we multiplied those together. They're nested. And this is going to give us a final of NM squared plus PM. The PM comes from populating the set initially. I'm not sure if I had the variables correct there, but any questions on this? Yeah, I think the only typo on the slides is this shouldn't be an M, this should be a P, because we're going through the prefixes vector, not the sentences vector. Or rather, not an R, but a P. Okay, looks like there's no questions, so we will continue. But quickly, any common mistakes? Yeah, so you could have used an unordered map as well, but really we don't care about the value. So an unordered set is not only more readable, but it's maybe better in memory. I don't actually know the implementation of an unordered set. Yeah, I think it'd be better in memory. And then you want to use the range-based constructor too, because you have the beginning and end for the vector. That's the quickest way to do it. It's optimal. And then making a new substring. Oh yeah, this is a big one. So what we did was we were constantly building up this string, pushing back a letter one at a time. If you created a new substring every time, that would be worse complexity, because creating a substring itself is, to do that, O of the length of the substring that you're creating. Whereas here, pushback is O of 1. And yeah. So let's talk about our agenda for today. So we're going to go over tree traversals, which uses recursion. Confusing at first, but it's very elegant and fun to play with. And then we're going to talk about binary search trees, which are types of trees, remember, that are sorted with a certain constraint. And then we're going to talk about AVL trees, which are balanced binary search trees. Okay, so let's go into tree traversals. Some terminology first. The root of a tree is the node with no parents, the first node. The leaf of a tree, or a leaf of the tree rather, because you can have multiple, would be a node with no children. An internal node has children, could have either 1 or 2, because this is a binary search tree, or not binary rather, but this is a each node has 2 children. Yeah, a binary tree. Thank you. So then we also have depth. And depth is the distance from the node to the root, while height is the distance from a node to the lowest leaf. And siblings have the same parent. So that's some terminology on trees. Okay, so warm-up question. Given a binary search tree with the following declaration, find the minimum depth of the binary tree. or given a binary tree, not a binary search tree, find the minimum depth of the tree, which is the depth of the shallowest leaf node. Okay. So if here's our function declaration right here, let's just redo that, int md, which takes in node pointer n. Okay, minimum depth. So the first thing we can do is say, well, if this node is null, let's just return. And then we have to consider a few cases. So we want to find the minimum depth, the depth of the shallowest leaf node. So how do we know when we have a leaf node? Well, it has no children, right? So there's really three cases if you think about it. Case one is we're looking at a node and has one child. And that child is its left child. Or we're looking at it and it has one child and the child is the right child, or has two children, right? I guess, or has none. So and we have to do like the min. So if we have a depth on the left and a depth on the right, we'd want to take the min of those two depths. So just writing out those cases, if we have a node left, then we want to return 1 because we're taking the depth, right? So we have to consider the current node that we're at, 1 plus md and left. Same thing with right. One plus md node right. And I can't get that. Okay, so that's the two cases if there's a node left and a node right. And then finally, there's either two children or no children. And we would just return, in this case, 1 plus the min of either one of those children, whatever one is less. So md and, oops, this would be min. And then we consider both traversals. So it'd be md and left and md and right. And I'm running out of room. This real quick. Okay. And just quickly, the reason that we had to separate the children is because if we just had this return 1 plus min and recursing down the left and the right side, if one of those sides didn't have a child, it would return 0. Oh, here we'd have to return 0. And then it would just take the min of 0. So this just guarantees that we're looking at leaf nodes. Okay, you can think about that. And then here is the answer there. Yeah. Okay, so tree traversals. 3 types, there's actually 4 types of tree traversals, and they differ in how they iterate through the tree. And there's a question, no. And how they iterate and visit, the nodes in the tree. So you have these pre-order traversals, which visit the parent and then the left and then the right node. You have post, which visits the left, the right, and then the parent. You have the in order, which visits the left, then the parent, then the right. And then you have the level order, which is kind of unique in its own way, where it just goes down the tree, starting at the top, and goes through every level, iterating left to right. So really how these differ is where you're doing the work. So like in the pre-order, you're doing work at the parent before you visit its children. And then also it's worth noting that these 3 you would implement typically using recursion, and you would call these depth first searches. And then a level order, you would implement using a queue, and we would call that a breadth first search. Okay, so let's just go through each of these. But before that, quickly, just to reiterate, the difference for those traversals is where we do the work. So no matter what, we're going to have this return statement if the node is null. Then we're going to traverse left and traverse right. But where we do our work determines where the what the traversal is. For example, if we do work right before the traversal to the left, right here, then that would be considered a pre-order traversal. And when I say work, it could be anything. You know, you could be adding integers, adding a sum. You could be printing out the value at the node. So for example, like see out the node. It'd be head val. And where you're doing that work kind of defines the traversal that you're doing. So the pre-order traversal, you do the work before you traverse to the left or the right subtrees. And in this case, the work that we're doing is printing the value. Print node head. So I have the function right there for the pre-order traversal. And then we have this tree. And I want you guys to tell me what the order of this pre-order traversal would be for the tree. Anyone? Feel free to throw it in chat as well. I think that would be a lot easier.
So would it be starting from the top, just 15, 6, 4, 5, 7, 23, 71, and then 50?
For the pre-order traversal, yep, that sounds right. And we can step through that just by going from the root. And if we look, the first thing we do is print it. So like you said, we print 15 initially. And then we traverse to the left. So we go to the left. And the first thing we do when we traverse to the left is print 6. And then what do? We traverse to the left. And the first thing we do is print 4. Then we traverse to the left and there's nothing there. So then we try traversing to the right from 4. And we get 5. And then we go back a stack frame and we traverse right from 6 and we get 7. And then you start going down the right subtree and repeating the process. Nice. Any questions on pre-order traversal? Cool. All right, so the next one is post order. And rather than doing the work before the traversals, we're going to do the work after the traversals. So just as before, what would be the post order traversal? Anyone? All right, Jake, let's hear it.
Isn't this one just reading the graph from left to right? So like 4, 5, 6, 7, 15, 23, 50, 71.
So that would be in order.
Oh, post order, my bad.
You're good. So we can walk through this one. So it looks like we're doing both traversals before we're printing the current node. So let's start at 15, our initial stack frame. And before we do any work, we traverse left and right. Okay, so we go left. We're at 6. Before we do any work, we go left. We're at 4. Before we do any work, we go left. Nothing. So we go back to 4. And we're still right here in this stack frame. We just traversed the left side, there was nothing there. So now we're going to the right side. And we're at 5. And before we do any work at 5, we try to go to the left, we try to go to the right, and there's nothing there. So the final thing we do is we print the node that we're currently at, then return out of that stack frame. So the first thing we do would be printing 5. We get back to 4. When we come back to 4, we've already traversed out its left and right subtree. So where are we at in the stack frame? We're at the print node. So then our order would look something like 5, 4. We jump back to 6. And remember, from 6, we already traversed down the left side. Now we have to traverse down its right side. So we go to 7. No children, so we ended up printing that. Get back to 6, print 6. And we get back to 15. But remember, we've only traversed down its left subtree, so we still have to traverse down its right subtree. And we continue that process down the right subtree and fill it up. And one thing that you'll notice is when we get to our final answer, the final node in the traversal is going to be the root of the tree, because it's going to iterate down all of its left subtree and all of its right subtree before it prints its own value. Any questions on post-order traversal? Cool. And the final one is in order. And we've already tried the front, we tried the bottom. Now we're going to do the work between the two traversals. So with in order, what would be the traversal for this one? And I think Jake already answered it, and he just read it essentially left to right. No, we go 4, then 5, then 6, then 7, and it would be in order going up. And if we step through that, we could see that, okay, so we're at our root 15, and the first thing we do is traverse left. 6, we traverse left. 4, we traverse left. Nothing's there, so we go back to 4, and before we traverse right, we print out its value. And then we go right. We traverse left, print out its value, go right. Jump back here. We've already went left, so we print out its value, then go right. Left, right, left, print its value, go right. We get here, and before we go down the right subtree, we print its node, we print its value. And you'll find that if the tree is a binary search tree, like this one, it will print out the tree in a sorted order. So I guess one way that you could sort, you can make a sorting algorithm that just creates a binary search tree and then does an in-order traversal. Probably wouldn't be that great, but you do that. Any questions on in-order traversals? All right, let's continue. So the final one is level order. Those first 3, we use recursion, and we would call those DFS, depth first searches. This one uses a queue, and we call it a breadth first search. You can also do the first 3 traversals using a stack, but it's called a depth first search. And that kind of makes sense, right? Because recursion or a stack data structure, both of those kind of use stacks, whether it's recursive stacks or a data structure that uses a stack. But here we have the level order traversal. And the unique characteristic of this, we said, was a queue. So we create this queue, we push the root into the queue, and then we have this characteristic while loop. It's saying while the queue is not empty, we're going to do a couple things. The first thing we're going to do is take the value at the top of the queue. Then we're going to pop the queue to get rid of that value, to only consider it once. And then we do our work there. Here, our work is printing that value. Then we say, if that value that we popped off the top, if that node that we popped off the top has a left pointer, has a left child rather, push that. If it has the right child, push that. And then what do? You go back up to this while loop and you continue the process. And that is a breadth first search. So we can go through an example of that. But first, I'll let you guys answer this. what the level order traversal would be for this? Feel free to throw it in chat. Or say it out loud.
I guess I can go again.
All right.
So it's just top down, left, right. So
Exactly.
15, yeah.
Yep. So top down, left, right. So he was saying 15, then it would be like 6, 23, and so on. Like that. So you visit like each row, like each level of the tree, left to right. And then if we look at the answer there, we would get something like this. So, just to visualize this in the queue, we can run through it a little bit. So if you have this queue, the first thing we do is we push in 15. Right here. So we push 15 in. And we say, while the queue is not empty, take the top value off. So our top value right now is 15. And we're printing it. So we print down 15 right here. And then after we print it, we say, does that node 15 have any children? It does have 2 children. It has 6 and 23. So we add those 2 to the queue. 6, 23. Okay. And then we repeat the process. We take the top one off. This time it's 6. First thing we do, then we pop it. Then we print it. We have 6 down here. And then we say, does it have any children? It does. It has 4 and 7. And we continue that process. So I hope that helps visualize the traversal. Cool. Any questions on the level order traversals? So when you're given a question, either just a coding question, could be on the exam, could be an interview. Lots of times it deals with traversals, and you have to think, what is the ideal traversal to use in this problem? And it really does just come down to, what is the order that I want to do this work in? For example, if I gave you a question that said, change every node's value to be the sum of all of its children, I just right off the bat, I would think, okay, so I want to keep track of the sum of the children before I'm working on my current node. That sounds like a post-order traversal, right? Because I'm traversing to the children before I do anything at my current node. So when you're getting these types of questions, go into your toolbox and think like, what would be the best traversal for this question, to answer this question? And here's another question. So minimum level sum. We're given the root to a binary tree, and we want to find the level of the tree with the minimum sum. So for example, we have 3 levels here, level 1, 2, 3, and the minimum sum would be the second level because it has, 0-based index, the first level, because it sums to 8, 6 plus 2. And the other ones would sum to values that are greater. So, going back to our toolbox, like, yeah, I could do a post-order traversal or an in-order traversal, but that would be pretty complicated. What would be the easiest traversal for this? What do you guys think?
Level order.
Level order traversal, exactly, right? Because that just seems like the problem set up to do a level order traversal. And then after that, the question would be, how do I figure out all the nodes in a given level? Like, we kind of have to clump all of these nodes together and all of these nodes together. And if we look at the code, the way that you do that is a for loop. So let's talk about this. Here is our minimum sum. The first thing we do is we push the root. And then we say, okay, the current level sum is 0, the sum of the current level. And the size of the level is the q dot size at every begin iteration of the while loop. So what does that mean? If we go back to our level order traversal here, when we just had 15, the size of the queue was 1. So really the size of that level is just 1. Then, when we popped 15 and we added both its children, we had 6 and 23. Before we do any work, if we take the size of the queue at that point, it's 2. So, and we also know that the number of nodes at that level is 2. So one way to figure out the number of nodes at a given level is just at the beginning of every iteration of your while loop, take the q dot size. Now that we're in our while loop, we can do this nested for loop. And we can iterate from I to the q dot size. And this will, encompass all of the nodes at that current level. And at that point, it becomes pretty simple. We have all the nodes at the current level. We just keep track of that sum. We see after we finish this for loop, if that sum of all the nodes at that level is the minimum sum, if so, save that level. And within that for loop, obviously you would be pushing back the left and the right because that's how the level order traversal works. And then don't forget to increment level at the end. So yeah, this inner for loop is kind of clumping together work to do all the work of the nodes of the given level when we're calculating the current sum for that level. Any questions to this solution? Cool. So yeah, using a for loop is a good way to keep track of all the nodes for the current level when you have to do work like that in these level order traversals. Oftentimes what we do is we push the root into the queue before we start the while loop. One thing to note, typically you don't know if the root is null or not, so I would typically recommend putting like an if conditional, saying if that root is not null, then push it. I think we just assume that it's not empty. Cool. All right, let's continue. So that is traversals. We have pre-order, post-order, in order, and level order. First three are breadth first search, depth first searches rather, and the third one is a breadth first search. The interesting characteristic of those is that, when we start at the root, the first few kind of like reach the bounds. They try all of the nodes in a given direction first. So like you'll see that with these depth first searches, you'll go like duh, 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 then duh. So you'll like go to the ends, go to the leaves of the tree, try like all the leaves of the tree in that order. Whereas with the breadth first searches, what you're doing is like you're actually only increasing your distance away from the root by 1 every time. So we have our root now, and then it's like, all right, now let's look at all the nodes 1 away from the root. So we'd look at 6, 23. Now let's look at all the nodes 1 away from those. So in applications that you want to find the shortest path, breadth first search is the way to go. If you remember from project 1 as well, remember how when we had the graph, the map, and we were having to use that search container, and we could implement that search container using a queue or a stack. Essentially what we were doing is deciding whether or not we wanted to implement it with a breadth first search or a depth first search. Okay, let's go to tree reconstruction. And the idea of this, it's a common exam question, is we give you 2 traversals and you have to reconstruct the tree from those 2 traversals. It's worth noting that in order to do this, we do need to provide you at least 2 traversals. Unless we give you some other constraints, like the tree is a binary search tree or something, because that would mean that you already kind of have the in-order traversal given to you. So with this problem, we could draw the tree given these 2 traversals. Post order and in order. So where do we start? What's the root of this tree going to be? One. How do we know the root of the tree is going to be 1?
Because in post order, it's the very last thing that you see.
Exactly. So we're given this post order traversal, and we also know that the last element in the post order traversal is the root. So we can just throw that down there. Now, where do we go from here? In-order traversal. When you're looking at a given element in the in-order traversal, everything to its left is less than it, right? And everything to its right is greater than it. So now that we have 1, if we look at 1 right here, we see that we have 4 elements to the left of it, and we have 3 elements to the right of it. So what this tells us is that we're going to have 2 children, 3 elements on the right subtree, and 4 elements on the left subtree. Anyone disagree with that? Okay, so now that we know, let's just do the right side first. Now that we know we have 3 elements on the right side, and those 3 elements are 6, 3, and 7. What is the root of that right subtree going to be? Well, we can just say exactly what we just said with finding the root of the first tree. If we know our values are 6, 3, and 7 on the right side of 1, the root of them is going to be the rightmost of those 3 in the post-order traversal. So we see 6, 3, 7, and we see that 3 is the rightmost value in that. So we know that the root of this subtree is 3. Now that we know the root of the subtree is 3, we can cross those 2 out. We look at 3 and we say, okay, well, 6 is on its left side and 7 is on its right side. That's easy. And that completes the right subtree. We know 6 is on the left side because in the in-order traversal, it's less than 3. And we know 7 is on the right side because it's greater than 3. So that's the right side of the subtree. And now let's go to the left. So we can get rid of all these elements, right? Because we dealt with all of those. And we have 8, 4, 5, and 2. Similarly, how do we know what the root of this left subtree is? It's the last value of those 4 in the post-order traversal. So it would be 2. Now that we have 2, we can see what's left of 2 and what's right of 2. 5 is the only element that's right of 2 in the in-order traversal. So we know that 5 has to be there. And now we know that 4 and 8 are to the left of it. Which one comes first is the next question. Well, we got rid of 5. We have 8 and 4. And of those 2, 4 is the last element. It comes second. So the root of that subtree would be 4. And then how do we know if 8 is on its left side or right side? We can look at it in the in-order traversal and see when we go to 8, or we go to 4, 8 is on its right side. Like that. And that would be the reconstructed tree from those 2 traversals. So really what we did here is we used this post-order traversal to figure out roots of subtrees, kind of recursively, really. And then from that, we used the in-order traversal to figure out if those elements in those subtrees were on the left or the right sides. Any questions here? This part's pretty tricky. Go on.
So does it change if we're given like two different types of traversals?
Yeah, for sure. So what if you're given in order and a pre-order traversal? The root is no longer going to be the last element. It's kind of like the first element. So if this was pre-order, what we'd say is like, okay, how do we know the root of this tree? Well, it's going to be 8. And then we're going to say, how do we know the root of the left subtree? It's going to be 4. So definitely, given your two traversals, your strategy is going to vary slightly. Any other questions? And like I said, you can always kind of expect that we're going to give you two traversals. Unless we say like, hey, this is a binary search tree. Because then we kind of secretly already gave you the in-order traversal. Okay, so that's tree traversals and it looks good to me. Yeah. Common exam question, but you'll get plenty of practice on that when you go through the multiple choice packet, preparing for the final. Now let's talk about binary search trees. So a binary search tree is a binary tree, but it has an additional constraint. What is that constraint? At any given node, all of the nodes in its subtree, its left subtree, are less than it. And all of the nodes in its right subtree are greater than or equal to it. That's our additional constraint for a binary search tree. So let's say that we have a node 5. 5's left subtree, we know would be no greater than the value 4. So it'd be 4 and less, given integers. And its right subtree would be no less than 5. It'd be 5 or greater for the keys, the values. So given a binary search tree, what would be the complexity of inserting for the best case, the worst case, and the average case? I guess what's the best case for inserting into a binary tree, a binary search tree?
O1.
O1, and when's that?
When it's empty.
Yeah, when you have an empty tree, throw a node in, O of 1 time. What's the worst case?
You have a lot of elements, I guess. So you have to go through each level and like insert when you have to insert at the end of the tree.
Yeah, when you have to insert at the end of the tree, what's the complexity of the end of the tree though?
Is it log?
It would be log if the tree was balanced, right? But what if our tree was just like, and we had to insert a new value right here? Then you'd be going through every element of your tree, right?
So O of n for that.
Mm-hmm. So inserting is O of n, worst case, and then you mentioned it. If it's balanced, it's log n for insertion. And then lookup. What are the complexities for lookup? And I'm not trying to trick you.
Once again, if it's empty, it'll be O of 1, right? Because there's nothing there. So it'll just return.
Yeah. Or let's say that you're looking for one element and it happens to be the root.
Yeah.
Or the worst case, if you're looking for that one element and it happens to be the very last element of the stick tree. Or the average case, you're looking for an element and it's somewhere in the bottom row because the bottom row has most of the elements of the tree. So similar to insertion, lookup would also follow the same complexities. Any questions on this? Okay, cool. Let's continue then. Okay, so let's talk about inserting and deleting into a binary search tree. Well, when we're inserting, all we have to do is just start at the root and compare our node that we're inserting to the current node. And if the node that we're inserting is less than the current node, we go down the left subtree. If it's greater than the current node or equal to, we go down the right subtree. And we just keep on going until we find an open spot. That's pretty straightforward. Deleting is a little trickier. When we want to delete a node from the tree, there's two situations. It either has, or three rather. It has 0 children, 1 child, or 2 children. If we're deleting a node that has 0 children, we don't have to worry about anything. We just remove it. That's all good. But, and you could say the same thing about 1 child. You know, if we're deleting a node with 1 child, well, you could just delete the node and move its child up. So where the node was, that's where the child goes. But if you have 2 children, it becomes a little trickier. If you're deleting a node that has multiple children, then you have to find its in-order successor or predecessor. And what that means is in an in-order search, like an in-order traversal, the value just below it or that's actually the value just above it or the value just below it. And we'll talk about how to find those 2 values. But what you do is you find that in-order successor or predecessor and you replace it with your current node. And if the in-order node had any children, you just move its children up to where it was because you're replacing it. So we'll go through an example of that. But first, insert. We have 4 values here that we want to insert: 3, 5, 6, and 9. And let's insert 3 first. So we take 3 and we compare it to 8. It's less than 8, go to the left. Less than 4, go to the left. Perfect, a place that we can insert it. Now we go to 5, compare it to 8, less, compare it to 4, greater. Cool, we can insert it there. 6, less, greater, greater. And finally, 9 is greater, less. So it looks something like this for inserting. Any questions on inserting? Cool. And the tree looks something like, oh, that's a different tree. Okay, so now we're given this different tree, and we want to delete these nodes, 5, 4, 8, and 11. And we said that deleting could be a little more complex, and we have to do different cases depending on the number of children. So let's go through that. And I just threw in the notes for deletion, so we can look at those if we need to. In this first case, we want to delete 5 from our tree. And we look at 5 right here, and we see that 5 has 1 child. So when the node we want to delete only has 1 child, that's fine. We just remove the node, and we put its child in its place. So now we're given this. And now we want to delete 4, right? 4 was next, right? Yeah. Now we want to delete 4. And in this case, 4 has 2 children. It has 3 and 6. So what do? We find its in-order successor or predecessor and replace it with that. So how do you find the in-order predecessor? You remember, the in-order predecessor is the node that comes right before it in the in-order traversal. And what you can find, what you'll do when you want to find the in-order predecessor is what you do is you look at your current node and you just go left once. And then you just keep on going right until you no longer have a node, right? Until there's no more right children. So you have your node. If there's a left child, you take that, then you keep on going down the right children until you can't go down any further. And that last node you're at would be the in-order predecessor. Similarly, if you want to find the in-order successor, you would go down to the right once. And then you would keep on going down to the left until you can no longer go down to the left. And the node that's there would be your in-order successor. So let's go through that. If we have 4, the in-order predecessor, we're going to go down the left and then keep on going down the right until we can't anymore. So we go to 3, and 3 has no right children, so 3 is the in-order predecessor. If we wanted to find the in-order successor, we could go down the right and then go down the left until we can't find any more nodes. In this case, we go down the right to 6, and 6 has no left children, so we just stop there. So 3 would be the in-order predecessor, 6 would be the in-order successor. And we can switch it with either. So in this case, let's just do 6. So remove 4, throw 6 up here. And then what's the final thing it says? It says remove the in-order node from its original spot, which we did, and replace its children, throw its children in that spot if necessary, but it had no children, so we didn't have to move those. And if it did have a child, it would only have one child. So we would just revert to the method that we followed in the delete 5, when we're just moving the child up to its place. And there's no problem with that. Okay. So we have this, we just deleted 4 and we're good to go. This is still a binary search tree. It looks like all the elements to the left of a node are less than, all the elements to the right of a node are greater than or equal to. So now we have to delete 8 from this. 8 is the root. Okay, so this is where that in-order successor and predecessor really come into play. In this case with 8, if we want to take the in-order predecessor, we would go left 1 and then keep on going right, but there's no right child. So we would take 6. 6 is the in-order predecessor of 8. The in-order successor of 8, we would go to the right once, and then we would keep on going down the left subtrees until we can't find any more nodes. So in this case, we'd go to the right to get to 10, and then 10 has a left child, so we'd go to 9. And then 9 has no left children, so we'd end there. So if we want to delete 8, we have 2 options. We can either replace it with 6 or we can replace it with 9. Let's replace it with 9. Actually, let's replace it with 6 because 6 has a child. So what we do is we just take 8, remove it, throw 6 in there. 6 had a child, so we just move its child up to its original position. And that's that. Tree still a binary search tree. And then if we wanted to remove 11, 11 has no children, so that's pretty straightforward. We just delete it. So here we cover the case where there is no children, we cover the case where there's 1 child, and we cover the case where there's 2 children. And the only time that you have to consider the in-order successor or predecessor is when you have 2 children. Cool. Any questions on this? We're kind of flying through this lab. I'm not sure if everyone just understands it, or maybe lectures are behind, or I'm explaining it poorly, but I guess we'll just keep on going. Okay, so that's binary search trees. And we talked about the complexity of binary search trees, and we said, when the tree is a stick, complexity is O of n for insert and lookup. But, what if we could avoid ever making it that worst case where it's a stick? What if we just always have it balanced? Then our lookup and search would also always be log n worst case. So what does it mean for a tree to be balanced? A formal way to define that would be for every node in the tree, the heights of its children differ by at most 1. So anytime you're looking at a node, its left subtree's height and its right subtree's height differ by no more than 1. And that would maintain this invariant that the tree is balanced. And what does that mean for the insert and search complexities? Like we said, we would no longer have to worry about those stick trees. So then worst case scenario for the insert and search would be log n. So let's go through that. AVL trees, we talk about, and this is our implementation of balanced binary search trees. They're self-balancing, which is pretty cool, at no extra cost to the overall complexity. And they can search, insert, and delete in log n time. And then the invariants are obviously the same invariants of a binary search tree. And also you have this balance factor saying that the balance factor must be in the range of -1 to 1. Because we said that, remember, the height, essentially what the balance factor is the height of the left subtree of a node and the height of its right subtree. And we said if we're going to keep those trees balanced, the difference in that height can differ by no more than 1. So that's our third, or rather our second invariant to AVL trees. In the STL, actually, it's not using AVL trees, but you could, if you wanted to, create a map or a set, not unordered, but regular map or set using an AVL tree. I think the STL uses red-black trees, which are just another form of self-balancing trees. But we chose to do AVL in this class because it's slightly simpler to understand. Okay, so remember from this slide, the balance factor must be in the range of -1 to 1, and we calculate the balance factor by taking the height of the left subtree and the height of the right subtree. Then let's talk about the insertion into an AVL tree. When you're inserting into an AVL tree, all you have to do is just insert it at its location and then rebalance it if you have to. When you're deleting from an AVL tree, it's the same as a BST. You know, if there's zero children, you're good. If there's 1 child, you just move the child up after you delete the node. If there's 2, you have to find the inorder or the inorder predecessor and the inorder successor. And then after doing that, you rearrange the tree. So we're going to cover how we rearrange this tree, how we balance it after doing these operations. So we can assume that the insertion or deletion was already done, and now we have to rebalance this tree. Okay. So this tree right here is not balanced. It doesn't look balanced. The left subtree looks a lot bigger than the right subtree. And to formally see that, let's calculate some balance factors. So remember, the balance factor is the height of the left subtree minus the height of the right subtree. So if you look at this node right here, it has a balance factor of 0 for its left subtree, 0 for its right, balance factor of 0. This node here would have a balance factor of 1 for its left subtree because it has a height of 1, if you look. And then it has no right subtree. So it'd be 1 minus 0 would give us +1. Here we would have 2 minus 0 because it has 2 nodes in its left sub, or a depth of 2 in its left subtree, like a height of 2 in its left subtree rather, and a height of 0 in its right subtree. So it'd be 2 minus 0, which would give us +2. And here we see that we have an issue because remember we said that if our tree is balanced, these balance factors can't vary by more than 1. And here we have a balance factor that's +2. So we're going to have to fix this tree and do a AVL rotation. So we acknowledge, first thing we did was we just threw in these balance factors starting from the bottom of the tree going up, and we found our point of issue, which is right here because we have +2. Now what do? Well, we know that our current node here is plus. Now we look at its child and see what its child is. 1 is also plus. So case 1 is when we're doing a rotation where your current node, your problem node, is the sign is positive, and its child node, the sign is also positive. And when you have the sign positive for the current node and the child node, what you do is a rotate right. And essentially what that is that child, that positive child moves up and the parent moves down to the child's right subtree. So this tree would become something like this, where the child moved up, 2 moved up, 3 became its right child, and 1 stays where it is. And now if you look at that tree and you try to calculate the balance factors, it will be balanced. Questions on this? Cool. So now let's go through a different case. And we can repeat the steps. Okay, so this tree doesn't look balanced. Let's calculate some balance factors. I'm going to do it slightly more quickly now. This is going to have a balance factor of 0. And remember, we calculate these balance factors bottom up. So 4 has a balance factor of 0 minus 1 equals -1. 3 has a balance factor of 0 minus 2 equals -2. We found our issue. We have a -2. And that's outside the range of -1 to 1. So our current is negative, and we look at our child. And our child sign is also negative. So case 2, it's negative parent sign, negative child sign. And when they're both negative, you do a rotate left. So the parent goes down, the child goes up, and the tree looks something like this. So if it was positive, positive, we did a rotate right. Negative, negative, we did a rotate left. Everyone happy? Okay, so those are the first 2 cases. Now let's go to the third case. If we calculate the balance factors here, starting at the bottom, we get 0, -1, +2. So now we have a positive and a negative. Our parent is positive, our child sign is negative. What do we do here? So in this case, we have to do a double rotation. And we have to correct the child sign to be the same as the parent sign first. So how do we do that? How do we turn this -1 into a +1? Well, we do a rotate left. So our first step in this case, when they're differing signs, is to rotate left. So we have something like this, where we took that child and we kind of rotated it left. Now, if you calculated the load factors here, you would have -1 for the child and -2 for the parent, or rather, sorry, +2 for the child and +2 for the parent. Now the load factors are the same sign. And we already covered when they're the same sign, positive, in case 1. So our second step of this process is our rotate right, starting at the parent. So our final tree would look something like this. So in this case, we calculated our balance factors. The child had a different sign than the parent. The parent was positive, child was negative. At that point, we said, okay, we're going to rotate left our child to make it the same sign as the parent. Once they were the same sign here, then we could just follow what we did in case 1 and do a rotate right. And now our final product after this double rotation is a balanced AVL tree. Any questions on that? And just to solidify this, let's repeat it. In this case, our final case, we would do the same thing, but in this case, the parent is negative and the child is positive. So it's going to be a double rotation where we're turning that child to be negative to match the sign of the parent. How do we do that? We rotate right. So 4 is going to go here, 5 is going to go here. And our tree will look something like this. Now, if we calculate it, this would be -2 balance factor. This would be -1 balance factor, same sign. When they're both negative, we do a rotate left. So our second step would be 2, 1, 4, 3, 5. And then the tree is balanced. Cool. Everyone happy? Any questions on this? Okay. In all of these situations, everything's great, but we never had this problem. Every time that we rotated a node, it only had at most one child. For example, when we move 4 up here to the position of 5, it had 0 children. But if we moved it up, 5 would become one of its children. So what if 4 already had 2 children? What if there was like a 3 here and a 6 right here? When we rotate it up, what's going to happen? Because 5 has to become one of its children. But it already has 2 children. This is a binary tree. So what are we going to do here? And that is our special case. When we try to move a node up that has 2 children. And what we do there, when a node already has 2 children, when we try to move it up, is we're going to have to pop one of its children and throw it on the node that we're moving down. So here's a good example. Our root has a balance factor of -2. And that's obviously out of place. We can only have balance factors of -1 through 1. So we look at its child and it has a balance factor of -1. So here we say, okay, perfect. We just have to do a rotate left, right? Because it's negative parent, negative child. But this is kind of confusing because we're rotating left, which means 4 is going to go to the root and 2 is going to go down here. But 4 already has 2 children. So there's 2 options. We could either get rid of the left child or the right child. When we're rotating left, what we do is we pop the left child off of 4. The node that's moving up, we pop off the left child. So in this case, let's pop off 3. So let's imagine that 3 is just not there. It's a left child. Now when we rotate left, we can just do what we did before. Pretty straightforward. 4 goes up, 2 goes down, 1 goes down, 5, 6. This is just like a rotate left like we did before. But we still have this 3. And the question is, where does 3 go? 4 moved up, it has 2 children. Can't go there. What we do is we throw it onto the node that came down. So 2, which was originally the root, that is now no longer the root, we can throw 3 there. And you'll find that when we have this special case and a node is moving up and it already has 2 children, when we're moving it up, if it's a rotate left, we pop off the left child like we did here. If it's a rotate right, we pop off the right child. But there's a problem here. What if that, how do we know that the node that's moving down has space that can take the child? When we pushed 4 up, we had to get rid of one of its children because it already had 2. But when we throw 2 down, how do we know it has space to take a child? Well, we know that because if 2 no longer has 4 as its child in this case, if we're moving it down, we're guaranteed that it had a child before and it has space for a child now. 4 used to be its old child. Now that it's no longer its child, it has space for another one. So it's not actually a problem. And you can always pop off a child. So this special case kind of makes it more confusing. I think if you work through a few examples, it becomes pretty straightforward. And it kind of just adds another element. So in summary, there's 4 cases, right? When you're rotating, you could rotate left or right depending on the signs of the parent and the child. And then finally, you have the special case that you have to consider. If the node that's moving up when you rotate right or left already has 2 children, you have to pop one of those children off and throw it onto the node that's going down. Kind of a lot to take in. Any questions on that? Okay. Final thing we're going to do today is this practice problem with AVL trees. And I'm going to give you guys maybe 3 minutes to try this on your own first. It's a difficult problem. I think if you're able to do this, then you really understand how AVL trees work in all of those cases. So let's take a few minutes where you guys can work through this, and then we can maybe get some answers and work through it together. I will be back in like a minute or two. Okay, how are you guys going? Have you had enough time to work through it? I just wanted to give some time so you can work through it on your own, and then we can do it together. No response. All right, let's do this. Okay, so the first thing we have to do is delete 5. 5 is the root. When we delete from a binary search tree, remember we have like 3 cases: 0 children, 1 child, or 2 children. 5 is the root, has 2 children, which means we have to take a in-order successor or predecessor. So we have 2 options. To get the in-order predecessor, we could go left and then keep on going right, which would give us 4. To get the successor, we could go right, then keep on going left, which gives us 6. Either one works. Let's take 4. So what we do is we take that predecessor and we replace our root, the 5, the one that we're trying to delete, with that predecessor. So this becomes 4, 3, 1, 2, 7, 6, 8. Right? I think it would have been a little less work actually to take the successor, because then you wouldn't have to rebalance the tree. But it looks like we're gonna have to rebalance this tree because the tree was originally balanced. Now that we deleted 5 and replaced it with 4, it would appear that the tree is no longer balanced, right? And we know it's no longer balanced because 1 has a load factor of -1 and 3 has a load factor of +2. Okay, so before we do any more work, now that we just deleted a node, we have to balance this tree. What case is this? Well, this is a plus negative case because we look at our root, not a root, but our node that we have to balance. And that's 3. 3 is +2. Then we look at the child, it's negative. So we have to make that child the same sign as 3. So a plus plus. How do we do that? It's going to be a double rotation. So this is going to become, we're going to move 2 to be, whoops. So we're going to do a rotate left to make both of those positive. So it's going to look something like this. And then after we rotated left, now we can do our rotate right because we have our balance factors are both the same sign. So then we can do our rotate right, which is going to look something like 2, 3, 1. Cool. And if you look at that tree, it's currently balanced. And we can check to see if it's a binary search tree. Still looks like a binary search tree to me. So that was the first step about removing the root. We chose to do that with the predecessor. Now we have to delete 7, which is right here. So once again, 7 has 2 children. So we could take the predecessor or the successor. Either one works. Let's take the successor, I guess. So we replace it with its successor, which is 8. And then we'd have something like this. Okay, and if we look at this, is it balanced? It is balanced, right? Yeah, looks balanced to me. So yeah, that would be a solution, I think. I remember it being more complicated than that. Did I mess up somewhere? Oh, you know what? Shoot. We made the problem too easy. We used the successor. We didn't use the successor. We used the predecessor. I was like, that seemed too easy. Okay, yes. So we told you to assume to use the in-order successor because it makes it a little more complicated. So let's take a step back and do it from the successor, not the predecessor. But I guess the predecessor made it pretty simple. Okay, so let's use the successor, which is right here. So if we're removing 5, we're going to swap it. So 6 is going to go up here. So it's going to look something like 6, 7, 8, 3, 1, 2, then 4. Something like that, right? Deleting 5, replacing it with its successor, which is 6. 6 had no children, so we don't have to worry about anything there. Okay, we look at this tree. Is it balanced? Well, if you look at load factors, it kind of looks weird, but this tree is balanced. I don't see any +2s anywhere or any -2s. So this tree is still balanced. We don't have to worry about rebalancing it yet. But now what do we remove? We want to remove 7. Well, removing 7 is pretty straightforward. All we have to do is just delete it and replace it with its child, because it only has 1 child. But this tree is not balanced anymore, right? And that's pretty clear because if we look at 6, if we look at the root, actually, not even look at the root. 2, 1, 2, 3, 4. 1 second. No, this tree is not balanced. This tree is not balanced here because if we look at our balance factor, if we look at 6, it would be 4 minus 2. So that would give us a balance factor of +2. And if we look at 3, it's going to be 2 minus 1, which would give us a balance factor of 1. My bad. So this tree is not balanced. So how do we balance this? Well, this is a plus and a plus, so we can rotate right. So this is before we're deleting the 7. So how do we rotate right? Well, we move the 3 up, right? So 3 goes up, and 3 had 2 children. So which child do we pop? Well, in this case, we would pop its right child. So let's just take that out right now. 3 moves up, it maintains its left child, which has a child itself. Then 6 moves down, and it still has its right child, 7, 8. Now 4, we popped that from the 3 when we moved it up because it already has 2 children. And what do? We add that to the node that came down. So 6 came down, we give it a new child, which is 4. And now if we look at this tree, 1, 2, 1, 2, 2, 2, 2, 1, 2, 3. This tree is balanced. Let's turn this into a 1 to make it look a little better. Okay. Then from here, we have to remove 7. And when we remove 7, all we have to do is just, it has 1 child, so we can move its child up, delete that, and throw 8 up here. And then that should give us, I hope, our answer. Yep, 6, 4, 8. Cool. So the tricky part here was when we had to balance after swapping the successor. And when we had to balance, since the 3, the node that was moving up, already had 2 children, we had to pop off its right child and throw that into the left child of the node that was coming down, which was 6. And that was the tricky part. And yeah, that's it. So if you can do a problem like that, you should be pretty good with AVL trees. I kind of struggled on it myself. And yeah, that's it for lab this week. Thank you guys for coming. And yeah, thank you.